Let's talk about these strategies here. Remember, I'm trying to get you ready for calculus. One of the best things that you can do is to be able to interpret a word problem. And I think this is a very solid strategy here, okay? Read that problem. I would suggest even maybe highlighting some things, okay? Make a drawing. You'll find the more you see me draw stuff, I am not going to be an excellent drawer, but I can draw something that looks like a rectangle, if they mention a rectangle, or looks like a cube. So draw that picture and then define your variables. What are the variables standing for? Maybe put them on the picture. How are they related to the picture? Because that's usually going to help you define some kind of formula that relates these items. And then you'll be able to solve the problem. So this is just a really good strategy they mentioned at the beginning of 3.2 that I think was a good thing to kind of, talk about. Now, I want to talk more about this little machine. It's a really good idea to think of a function as an input-output machine. Okay, so I'm going to give you a silly example, but it kind of will make sense a little bit, hopefully. An oven is a machine, right? I'm going to take chocolate chip cookie doughs. I'm going to put them in the oven. The oven's going to do its thing. It's going to output some chocolate chip cookies, right? Now, if I input sugar cookies, the sugar cookie dough in, it's still going to do its thing, but now my output's going to be sugar cookies, okay? So there's a difference between what we put in and what we're going to get out. But the rule of the machine, the function itself, is going to represent some kind of rule that says, if I put in this input, this is what you do. If I put in this output, this is what you do. So this is a really just a nice way to think about it. And so I always try to include, when we're dealing with functions, that sort of thinking, okay? Now let me remind you some of the terminology we've already discussed. Independent variable is our x, or whatever they define as our x, depending upon if they say in terms of, or if they say a function of, that would be your x. Y is the same as f of x. Now, it's not always an f function. Sometimes they call it a g or an h. It doesn't matter. That's your rule. What is your function's purpose? What does it do to that x when we input it? That's our dependent variable. And I think about the fact it depends on what I put in. So our x is our cookie dough. If I put in chocolate chip cookies, it's one thing. I get something different out. Remember, this notation means exactly the same thing. xy could be written as x f of x. On a graph, think of f of x as your height at that particular x. The power of function notation is that function notation is going to give you so much information all at once. It's going to give you, what function am I using? Am I using the oven or am I using the refrigerator? Okay, what rule do I have? But it's also going to tell you what x I am looking at. Am I putting in the cookie dough that's chocolate chip cookies, or am I putting in sugar cookies? Okay, so we say in this particular case that y is a function of x. The domain are the inputs. What can you put in that machine? What do you put into the oven? That's your input. Output. If the oven does its thing, what do you get out? So remember, domain are the input values, our x's, range is going to be our y's. On a graph, the domain will look at from left to right is the best way to kind of describe how to look. What are the x values I use from left to right? The range on a graph, I think of bottom to top, low to high. What are the heights from the bottom of the graph to the top of the graph? So that's your input output, okay? So that's just some terminology we've kind of been touching upon. You probably learned that stuff in your Algebra 2 course, most likely, but you all came from lots of different places. So I never assume anything. So I'm always going to kind of introduce you to those topics or review those topics as we get to them. Now, 3.2 in iMath has a lot of stuff in it. Domain and range and things, interval notation. We will touch upon that. You just got to give me time. There's only so much time in a class period, but we'll go over those things as we get an opportunity to. Do we have any questions about any of the stuff you see here, any of the terminology you see? Any questions at all at this point? Okay, I'll make sure everybody's on the same page. And then I believe we go to the investigation. Yeah, okay. Okay, so if you're writing in your book, open up the 3.2 investigation. But I've provided the digital copy too if you wanted it. Okay, so let's talk about the box formed by cutting the squares. Okay, so let me remind you of the box. Okay, so we had a sheet of paper. We cut out some square. We call it, X. They call the length X by X. Okay, and then you might have discovered, remember, from 3.1 that longer side, that 11 inches, we had to take off 2 X's. The 8.5, we took off 2 X's. And then if we fold it up, we get that the height is X, the length is 11 minus 2X, and the width is 8.5 minus 2X. So that's where those come from. Just you kind of have to use logic of you make the box. The good old open box problem, cutting out the corners, it's a common one when it comes to calculus because there's nice things you can do to the problem when you get to a calculus level. Okay. Now, so that's where they got this equation. You'll see volume is length times width times height. And remember, multiplication is commutative, so it doesn't really matter the order in which you put those things in. You decide. And let's go ahead and look at our first one here. It says for each value of X, determine the corresponding volume in cubic inches. So I'm going to do the first one with you. So where the X is sitting, use substitution. We're going to get 1.5. Sorry, I somehow switched colors. I think my bracelet did. And then 11 minus 2 times 1.5. Watch when you put it into that parentheses that you follow your order of operations. Minus 2 times 1.5. Trying to make it a little more consistent. Wait a second, guys. Okay, and so what we get is what we see here. Now, remember, no matter if you're in an Algebra 1 class or if you're in a Calc 3 class, order of operations lives on forever and ever. You got to follow all those rules. So what's the first thing we have to do within those parentheses? What are you going to multiply? Tell me. Yeah, exactly. So 2 times 1.5, if you just double 1.5, that's 3. That's a nice one to double. And so that's just 11 minus 3, or 8. So I'm going to write over here to the side, kind of small here. 1.5 times 8. We're going to do the same thing. So you're still going to get that 2 times 3, or 2 times 1.5 is 3. 8.5 minus 3 is your 5.5. And if you do that multiplication, we get 66. Now that's in cubic inches because it's the volume of a box where the sides were described in inches, so inch by inch by inch, cubic inches. Now for the next one, please try it on your own. The substitution, see if you can do the math on your own. I'm going to display it for you. I want you to see it, but if you could give it a shot yourself, you can grab a calculator if you want one. Yeah, and always, when you walk in, you're always welcome. There's scratch paper, pencils, calculators back there. You're welcome. So I'm going to do it. Just look down. When you're ready to look up, go ahead and look up. Then we can check to make sure you're doing your order of operations okay. And when you're ready, look up on the board, see if we got the same thing, and it's looking good. Lovely, lovely, lovely. So I think inputting into a function is pretty nice for you guys. So I think we have maybe one more person finish it, and then we'll look at B. Okay, now B says, is it possible to use the formula to represent the value when x equals 1.5 without actually calculating the value? Well, I mean, that's kind of what we did when we first just inputted it. But you might recall back in Algebra 1, Algebra 2, whenever you were introduced to functions, you could make it v of, that's one way. You can call some function, f of x equals that whole thing, v of x, whatever. But if you say v of 1.5, that's saying what is the volume at an x input of 1.5. Now, obviously, we know the answer now, right? We know that the answer was 66 cubic inches. So we have some context there. We know earlier that 66 meant something in relationship to the 1.5. And on the graph, we should expect, if we had a graphical representation of that we should see that at 1.5, our independent variable, our x, we should have a height of 66, okay? And then let's look at this one. See how the volume went down when we cut out that square that was 3.1 inches. Everybody okay with 1A and B? Okay. And that's what they're getting to for C. They actually called it f of x, not v of x. If I was doing it on my paper, I probably would have called it v of x so I could remember what the heck that function was doing. But f of x is fine. You could call it really any variable you want. They're going to use f of x a lot. That's a very common notation for a function. And it says here that function notation provides a concise way to reference the value of a dependent quantity that is associated with a particular value of an independent quantity without actually computing its value. Okay? They call that notation, please make sure you highlight, write down something, f of x. That's the way I'm going to read that, f of x. That's the most common way it's read. Sometimes you could say the function at x, the function f at x. That's a little more, and mathematicians usually aren't going to find the wordiest way to say it. They're going to say it as concisely as possible. So that f of x is common. So if we look at C and then the I think I must have cut something out there, but if you look at this one, what does f of 1.5 represent in the context of the box problem? Can anybody tell me, what would we say that means? What does that mean? How could you put that into words of what that is representing? Could I have somebody share their idea for me? Got an idea? What would f of 1.5 in this box problem mean? Yes. Yes, that's the way we would read it. So that would be the answer to that, f of 1.5. But what does it tell us? Yes?
How much we took away from the side.
Okay, so it gave us the side length of the square. But what you have to realize is that notation means f of 1.5 is the volume when the side is 1.5 inches. So there, remember, that f of 1.5 represents the volume when x is 1.5. The f of, put in front there, that function, what function do we use? We use the volume function. What are we going to input? 1.5. So you have to be a little more mindful of what those things mean, okay? And then that moves us on to 2. Does anybody recognize this? Have a sort of idea of what's going on there? In 2 there. It says, what does f of 3.1 minus f of 1.5 represent? And that's how you would read it. F of 3.1 minus f of 1.5. The difference of f of 3.1 and f of 1.5. You got it. It's the change in volume. For what x values? 3.1 and 1.5. For squares with sides 3.1 versus 1.5. It's the change in y. Remember that, delta y? Right? Instead of writing y2 minus y1, we're going to put it in function notation. We're going to do f of x2 minus f of x1. But it's the same thing. We were finally getting used to that delta y notation, and they had to throw some other notation in there. What is y2? The function at x2. What is y1? The function at x1. But it's the same notation. But what does it give us that's so great? We know what function and the x values all at once. So that notation is just pretty powerful because it gives us lots of information all at once. Does that make sense? So that change in volume, that delta y, it's important that we still know how to find that in the context of a function. It's just, we might use function notation. That's the main difference. Everybody okay with those? Do we have any questions, concerns? Anybody have any questions about that? Okie dokie. Here, there's not much that I highlighted domain and range, and but I wanted to talk about this. This kind of broke down some things pretty nicely for you. Okay. The whole thing is the function definition. F of x equals that. So it's the formula that for that particular function. The rule for which function is it going with? It's going with f of x, g of x, h of x, v of x, whatever you want to call it. Remember, this is the name that they have given the function. F is very common. It doesn't have to be an F. Use the notation, the function name, or the any variables that they have used in IMath. Use whatever they've used. Remember, the input is your independent variable. That's this x right there. The output is your y in most case, if we're putting it on a graph. That's going to be your y value. And in this case, we can call it f of x. So it just kind of gives you what it's related to. Now here they said f of x is going to be equal to our volume. So they've given us that relationship very clearly there. Okay. So there's not too much there with all the stuff we've kind of been talking about. But now I want to move on to number 2. So we've got this f of x function related to that box's volume, cutting out the corners from an 8.5 by 11 sheet of paper. And it says, what is the independent quantity? So based on what we just talked about and everything we've talked about when we've dealt with independent input quantity, what's our input? What is our input? What's our input for this function? What's going into our function? You guys are being all quiet today. What's the input of our function? Look at our function. Here's our function. What's the variable we're inputting into the function? What variable goes into that function? X. Don't make it harder than it is. What does X stand for? What have we said the X is standing for? The length of the sides of a square. Yes. So this is the length of a side of the cut square. You'd think after writing for so many years for students it'd be neater, but okay. Number 2, what does f of x represent? So now we've stuck in some value of x. What does f of x tell us? Tell me. Huh? No, it's died. Now it's going to be this weird swirl in the middle of the video. What does f of x represent? What is f of x? The box's volume. So you see how they also wrote up above that f of x equals v, which is the box's volume. What units did they use? What? So inches for the length. So what would the volumes? Cubic inches. So let's put that on there to remind us. It's always important to remember those units, remember those things like that. It's helpful, okay? So what does f represent? What is the function doing? It's kind of the same thing as 2, I believe. That's just how they have named the function. Sometimes you can say, you know, that is our output of the function. And then that comes to the domain of f. Okay, now let's go back to my beautiful little box. What if I cut out, I hope those are close to being squares. What if I cut out a square that had 0 length? Is that something that we would do? Could we fold up the box if I cut out 0? No. But could I cut out, if I had very beautiful, wonderful, magical scissors, could I cut out a little square that was 1/10 by 1/10 of an inch? Yeah, sure, you know. So anything that's just above 0, I can do, okay? Now, that leads us to interval notation, which we're going to talk about a little bit more as we go, okay? So we know the domain won't include 0. So you might recall from Algebra 2, a bracket says I include it. A soft parenthesis, a rounded parenthesis means I do not, but I'm super close. I could be 0.10, 0.001. I could be a little close, okay? Now, let's think I'm going to keep on whittling away at this. So now I made one that was 3 inches. So it's 3 by 3. Now I only have 8.5 to go. What happens when I'm at 4 inches? Think about, you'll have like a little teeny strip right there. What happens when I'm at 4 1/4? What happens when I'm at 4 1/4? This is 8.5. What happens if I'm at 4, if I hit 4 1/4? I cut it completely in half. Would I have anything left to fold up? Because I'd cut it, I'd chop it. So 0 doesn't work because it makes it so you can't really fold it. And if I cut out the squares, there's no real paper left, there's nothing to fold it. And that's exactly at the halfway point. So if you solved it mathematically, you would do 8.5 minus 2x equals 0. Where does it equal 0? That's going to mess it up. So anyway, 4.25. So we can go almost to 4.25. It would be a weird shaped box. 4.24 would work. It would be kind of strange looking, but it would work. These, remember, that parenthesis notation means don't include it, but you're super, super, super close without touching it, okay? So 0 doesn't work, 4.25 works. Remember, an endpoint of an interval, that is all the values in between. That's not a point. That is, I can go anything to the right of 0 and stop just before I hit 4.25. So 4.244, 4.25555, yeah, stuff like that, okay? Okay, so that's domain. We're going to talk about domain more and more, so don't fret. That will happen. Okay. So then I think it's a good idea to look at what this represents on a graph. So everybody, look at your graph. Let's talk about how we look at the graph. It says illustrate each of the following on the graph. So let's start with this one. 3.5, f of 3.5, okay? So go over to your graph, find an x value of 3.5, go up to the function where it's drawn, and let's color in that dot. Now that's 3.5 comma f of 3.5. We plugged a 3.5 in earlier. Did we plug in 3.5 earlier? No, it was 3.1, 3.1. Okay, so if you plug in 3.5, you do get 20. So let's rewrite this as the point 3.5, 20. They both mean exactly the same thing. I'm going to mark that on the graph. Now, let's think about how 2 and 3 are different. 2 and 3 are different because one says, what is f of 1.5? And one says, find the solution to f of x equals 40. It is very important that you know the difference between those two things. Okay. 2, f of 1.5. What is our x value? 1.5. You may recall we did do that earlier. But if you go to the graph and you find 1.5, you go up to the graph, that is really saying the height at an x value of 1.5. And you'll notice that its height is 66. That means that the point 1.566 better be on the graph. If it isn't on the graph, then your algebra was wrong earlier, or the graphic interpretation is wrong. What's great about algebra and the graphical interpretation, the geometry of it, they better go together. Many times if you have a complicated algebraic equation, using Desmos or some type of graphing utility will be very helpful because the algebra should relate to the graph and the graph should relate to algebra, or one of them is wrong. So they should go together. Okay. Now let's look at this next one. It says find the solutions to f of x equals 40. Remember, that means where is y 40? Where is the height 40? So go over to your graph. Let's highlight the 40 line. There's the height of 40. So that is saying, where on the graph is the height 40? You notice that functions have to pass the vertical line test. Vertical lines only hit them in one spot. Doesn't have to pass a horizontal line test. So it can have more than one answer. This does have two answers. Can somebody give me one of the answers? And you may guesstimate. We're going to have to guesstimate it. They're not quite where we want them. Can somebody tell me one of the answers? It's going to be x equals 0.5. Well, okay. I'm going to be a little bit picky. Did it hit 0.5 perfectly? Let's just go one more. Let's go 0.6. I think it's scooched in a little bit. Okay. Can somebody give me the other one? What's it? You see 2.9. Great. Now, because we're guesstimating, and if we didn't have a function that was easily solvable and we just were using the graphical interpretation, if you said 2.9 and I said 2.8, it's okay. Guesstimate to your best of your ability. Okay? Okay. Everybody okay with our answers there? 0.6 and 2.9. Those are the x values at a height of 40. That's the best way to think about it. Those are the x values with a height of. F of x is the heights on the graph. The heights on the graph. If you start to think of it in that way, that will help you as you go through this process. Okay. Now let's talk about this next one. This we've already done, but we haven't done it quite in this notation. Use a function notation to represent the change in the box volume as the length of the side of the square cutout increases from 2 to 3.5. Then represent this change on the graph that is given in part B. Okay, so here's what they want to look at. Do you remember good old delta y over delta x? That average rate of change? We have done this before, but they're going to use function notation. F of x2 minus f of x1 over x2 minus x1. Could we write that notation down for me? Okay. So f of x2 minus f of x1 over x2 minus x1. That's that average rate of change between those 2 points. The slope of the line if we connected those 2 points. Okay. So let's think about what they want. So let's do what is f of 2 and what is f of 3.5. F of 3.5 was 20, right? F of 2, was that the one that was, did we do f of 2 anywhere? Okay, let's guesstimate from the graph then. You think 63? Okay. We have a function we could use, but let's do that, okay? So now, This is going to be, remember, it's ending minus beginning. We're going to go for the x's from left to right. Okay, you want to go from your x's from left to right. Your y's will do what your y's will do, but your x's should go from left to right. So that means we want this to be our x1 and this to be our x2. So we're going to be 3.5 minus 2 over f of 3.5 minus f of 2. So that would be, let's see, that's 20, I'm sorry. So that would be 20 minus 63 over 3.5 minus 2, which is negative 43 over 1.5. Or, okay, let's just double everything, negative 86 over 3. And then if we connected those points, and please, you know I can't make a straight line. Even with technology, I'm not the best. Oh, there we go. Okay, that's kind of, that would be the slope of the line connecting those two points. And so that sometimes they'll refer to that as a slope of a secant, the average rate of change between those 2 points. You can also even put the, I know that iMath sometimes has you put the delta y and delta x on the graph. Now in this case, that would be the change in volume over the change in, I guess we'll just call it x, because they call that side length x. So you'll notice that we went down. That's what that negative 43 represents. And then we went over to the right 1.5. So it's just the slope of the secant connecting any 2 points on the graph would be the average rate of change at that particular spot. Okay. Any questions on how we did that? You get my quiet crew this period. Yes. She's watching, making sure, see what we're doing in here. We're doing amazing, wonderful stuff, right? Okay. So 3 things they're trying to remind you of. Domain are the independent values, those inputs. Range are those dependent variables, those outputs. The rule is what your function rule happens to be. In this case, we've been doing a lot with that volume is our rule. Okay. Now, I'm not going to worry about 3 there because we don't have a ton of time. Do we have any questions? Do we have any questions at all before we move on to one of the pre-course things? And are you good? Okay. Okay, so now open up your iPad, open up iMath for me, please. Yeah, please. No, don't turn it in yet because we're not done with these. We'll continue for the next few days because we still have a lot of stuff to talk about. So this will be turned in probably Thursday, I'm thinking. Okay, so could you please open up your iMath and open up the pre-course M32 day 2. There were 2 due today. One of them you should have done yesterday, the pre-course M32. And then the pre-course M32 day 2 is also due today, I believe. So again, remember, when I'm walking you through this and we're talking these out, your numbers and my numbers might not always match. Sometimes they do, but not always. So please adjust and ask questions as you go. But I'd like to walk you through these because some of the way they're wording things are a little funky, and I think it helps a little bit. Okay. So we have this function, f of d is 1/4 square root of d. So I'm going to write this function down over here. If you have a sheet of paper, write this down. And let's write what we're telling us everything is, okay? F of d is used to determine the amount of time in seconds that it will take an object to hit the ground. So F of d is seconds to hit the ground. And then d, they said, is the height that they dropped the thing from, and they did that in feet. So you always want to relate the function with what's my input, what's my output. What's my input there? What's my input to this particular function? What do you think is my input? D, which is
The height.
the height at any particular, whenever we're dropping it, okay? What is my output? What is my output?
The second.
The seconds. So you can also remember, even write that as input is your independent variable. So that would be feet, and then seconds would be your output. Okay. So these ones here, we're just going to enter those into the formula. Let me kind of show you some hints of what iMath is doing. First off, can we plug -1 into a square root? No, we can't get a real number. You'll get a rational number, but as far as a real life application, can we use that? No. That's that irrational I. So no, we can't use that. Now they said for iMath, just put DNE for does not exist. But we can plug in anything that is a positive number or 0. Because like, what's the square root of 0? Yeah. So 1/4 of the square root of 0 is just 0 times 1/4, 0. And then just go down your list. Here's the one I wanted to talk about. Now, my list and your list might be slightly different. So account for the fact I don't know what yours says. But let's say you got to 3. If you put in 1/4 square root of 3, iMath will do the math for you. You don't have to actually throw that into a calculator. It will do it. But you might, there's, that little yellow box. Hit that little yellow box. Or I think the abbreviation for square root is, they use squirt, SQRT. SQRT will work. Yeah, especially if it's more than one digit thing, okay? So be careful with how you enter it. So I'm just gonna go down my list. Again, your numbers and my numbers are different. I'm gonna fill mine in. You go ahead and work on that list. And I just kind of put down what I think iMath will accept. Again, your numbers and my numbers are probably different, so be careful. Okay. Now let me tell you about the graph. Anybody stuck on anything? Anybody need help with that part of things? We good so far? Okay. Now let's look at the graph. See that graphical interpretation underneath? Again, you have the ability to do this part. I can't. But I will tell you, iMath, because I did play around with it earlier, I put in my 0, 0 point, and I put in 4 1/2. Those ones it accepted very nicely. Because iMath, it can be, it can't really be more accurate than a half. So I chose those numbers because they came out really nice in iMath. And then it made that swoosh to the right, which hopefully you know what those parent functions look like. And we're going to talk about those parent functions more. Eventually, we're going to get to those. Okay. And then they asked some questions. So everybody in the same spot with me now? Okay. So now they've asked some questions. Let's talk about the questions. Okay. State the function's practical domain and range. It should be noted that this model ignores air resistance. The lower bound for the practical domain is, okay, your options are D is less than 0, D is less than or equal to 0, D is greater than 0, D is greater than or equal to 0. Did we discover that the distance, the height we're dropping it, is it allowed to be negative? No, we're not going to drop it from underground. That doesn't make sense, does it? Could we drop it from the ground at 0? Yeah, it works. Does it give us much of anything? No. But at 0, 0 is a legit point that we can plug into our function. Could we plug in 1,000,000 if we wanted to? Yes. Are we going to get 1,000,000 feet in the air? No. So here's what they want, I believe. They want that D is greater than or equal to 0. That's what they want here. D is greater than or equal to 0. We knew that. So don't forget the one that says greater than or equal to. And the upper bound is determined by whatever we say the maximum height happens to be, right? If we're dropping from a building that is 200 feet tall, that's our maximum. So find the one that says It's determined by the maximum drop height. In real life, we can't go up to infinity, but the domain in real life, mathematically speaking, if it wasn't a word problem, we already said we can go to and start at 0, and we can go to infinity. Infinity always gets a parenthesis. We can never land there. We can keep going and going and going and going. The bracket, remember, is the one that says, hey, I can use that number and anything after that. Remember, that is an interval from 0 to infinity, means my graph should go from 0 to the right in the positives for as far as I want to go, okay? Then let's look at this next one. The lower bound for the practical range is, again, our time started, our height starts at 0. So same thing. Our time is greater than or equal to 0. And in real life, we're kind of restrained by the maximum wait time. What's our maximum height? Well, it depends on where we stop. So they said it's determined by the maximum wait time. I think it's dependent on the other one, so I believe it should be. But anyway, that's what they said. So please put that, and then we can have that discussion later on. Same thing. The y's start at 0, and they can go as high as we want. So for a domain and range, we think of bottom. Our lowest is 0, our highest. That little thing's getting high pretty slow. But if I put 1,000,000 in, I'm going to get 1/4 of the square root of 1,000,000. That's a big, big number. It can get really, really high, okay? It's allowed to. And that's what that tells us. Okay. Now, the next one, you have to plug into the function yourself. I don't know what your number is. Mine was 57. So I'm going to do that 1/4 of the square root of 57. Now, take that decimal place, if you could, out like 4 places, or you could put the exact value in like I just had it. If you use that little math box, you can do that. Let me tell you what that is. Mine, I'm going to tell you what mine is. Yours, again, I don't know what yours is. Okay. So, what do we know our point was earlier? Do you remember? This was feet. This was seconds. So the 57, our input is feet, right? Our output is seconds. So let's put the little second there. At least I'm going to write on mine. You can't really write on yours. But which one of these is true? Is it 57 feet, 1.89 seconds? Or is it 1.89 feet and 57 seconds? Which is the best one to pick? For me, that's the one that I have to pick. Now, again, yours might be slightly different numbers, but that gives you an idea, okay? Now, here's where E is different. Remember that one where it said, where was the f of x equal to 40, I believe it was. That's the same thing here. They are saying that my seconds are equal to 5.9. So that's different. Now, we know that our formula is 1/4 square root of d. So we could use mathematical techniques to solve that for d, couldn't we? We could rearrange that and get a new formula that's related to d. So it says we can substitute 5.9 for f of d and solve the resulting equation for d, and that's the one that I have to pick. So hopefully that you finished that. Do we have any questions about that pre-course one in iMath? We good? So you have a few minutes, not very much. We're almost out of time. But working on your iMath, you do have some iMath homework due, I believe, Saturday. All your pre-courses should have been turned in, right? I think all those are turned in already. We'll turn these notes in again, I think Thursday, based on what I'm looking at, okay?